Welcome back to The Explainer. If you're gearing up for a machine learning interview, or maybe you just want to finally understand how modern speech-to-text models actually work under the hood, well, you are in exactly the right place. Today, we're building a comprehensive study guide on Connectionist Temporal Classification, which is way more commonly known as just CTC. My absolute goal here is that by the end of this explainer, you're going to have that massive aha moment, and the magic of CTC will be completely demystified for you.
Okay, let's dive into this. Here is our roadmap for today. First, we'll look at the frame alignment problem. Second, blanks and the collapse rule. Third, summing paths for CTC loss. And finally, we'll wrap up with the conditional independence limit. Section 1, the frame alignment problem. This is the big hurdle it overcomes. To really appreciate CTC, we have to understand the huge, massive hurdle it overcomes right out of the gate in speech-to-text. Think about it. Your audio track is chopped up into thousands of tiny frames, but your text transcript, it has way fewer tokens. And crucially, you don't actually know which audio frame maps to which text token. In the old-school hybrid ASR approach, you needed incredibly complex indirect alignment steps just to generate a specific phonetic label for every single frame. I mean, it was a total manual nightmare. But CTC, it handles this unknown alignment completely automatically. You're just training directly on the audio and text pairs. I really want this to sink in, so we're making it the thesis of the day. CTC lets you train audio to text without frame-level alignments. Actually, literally. If you remember absolutely nothing else for your next interview, remember that CTC is entirely alignment-free. It's essentially a loss and output layer that completely removes the need for those expensive, rigid frame-level alignment maps. It's a real game-changer. Moving right along to Section 2, blanks and the collapse rule. Let's see how this alignment-free magic works. So how does this actually happen? Let's follow the journey of a single word. It relies on the model doing something very simple, emitting one token, or a special blank token, for every single audio frame. But since there are way more frames than actual text characters, the model clearly needs a way to shrink that sequence down. And it does this by applying what's called the collapse rule, which has two beautifully simple steps. Step 1, merge any repeated symbols. Step 2, remove the blanks. And this brilliantly illustrates exactly what we mean. Let's trace the journey of the word cat. Imagine our model processes 9 audio frames. The raw per-frame output is a total mess. C, blank, A, blank, T, blank, right? 9 messy frames. Now, we apply step 1 and merge the repeats. So those 2 C's become 1. The 3 A's become 1. We get C, blank, A, blank, T, blank. Then, step 2, we drop the blanks, and boom! Those 9 messy frames neatly collapse down into the 3-letter word cat. Now you might be wondering, wait, why do we even need that blank token at all? Why not just merge the repeats and call it a day? Well, the blank token is absolutely the secret sauce of CTC. Think about a word like hello. If the model just spits out H-E-L-L-O and we simply merged all the repeats, hello would incorrectly collapse into helo with just one L. So to prevent this, the model outputs an L, then a blank, then another L. The blank literally separates genuine repeated characters so they actually survive that merge step. It also just gives the model a really handy way to say, hey, there's no output here during a pause in speaking. Section 3. Summing paths for CTC loss. Let's talk about how the system actually learns. Okay, so we know how a sequence collapses to form a word, but here is the critical interview question you absolutely need to be ready for. How do we calculate the loss and train the model if we don't know the exact rigid map of the audio frames? Basically, how does the model know if it's actually doing a good job? Here is your zero-math mental model for CTC loss. The probability of the text is defined as the sum over every single frame path that collapses to the correct transcript. Let me explain that. Think of the loss function as this omniscient observer. Instead of forcing the model to take one specific rigid path, like dictating, hey, the letter C must happen exactly on frames 1 and 2, CTC just looks at all valid routes to the destination. It considers every single plausible alignment at once and just sums them all up.
So the crucial point here is, we don't actually calculate every single one of those millions of overlapping paths manually, because let's be real, that would take forever. Instead, CTC computes this super efficiently using a clever grid walking technique called the forward-backward algorithm. It uses a dynamic programming grid, a trellis of frames by tokens, to calculate the total sum without ever explicitly listing out all the individual paths. And the best part? It needs absolutely zero explicit per-frame labels to do its job. It's really just a brilliant mathematical trick to evaluate performance without needing a map.
Finally, Section 4, the Conditional Independence Limit. Time to look at CTC's biggest weakness.
Because, every hero has a weakness. Up to this point, CTC probably sounds completely invincible, but it does have one specific, heavily tested flaw that you absolutely must understand: conditional independence. Because CTC processes everything strictly frame by frame, it assumes each frame's output is completely independent of the others. What does that actually mean? It means CTC lacks any internal language model. It doesn't intuitively understand the context of the words it's forming. It doesn't know that the letter Q is almost always followed by U. It is just blindly looking at the raw audio, one isolated frame at a time.
So let's weigh this out. CTC's strengths are undeniably massive. It's simple, it's incredibly fast, and it's monotonic, meaning the audio frames map left to right without any confusing reordering. It's also highly streamable. You can just emit outputs per frame as the audio arrives in real time. That's why it's the standard fine-tuning head for massive models like Wave to Vec2. But the limits, they are very real. The conditional independence assumption is super strong. It simply cannot model dependencies between the output tokens. In practice, to compensate for having no internal language model, we usually have to pair it with an external one during the final decoding phase, a process called shallow fusion, just to give the system some much-needed contextual awareness.
Now, what's really interesting about this slide is the industry fix. If you really need to solve that no internal language model problem without just, bolting on an external one, the answer is RNNT. RNNT takes the brilliant alignment-free foundation of CTC and directly adds a prediction network to it. That prediction network essentially acts as an internal language model, stepping right in to fix CTC's exact contextual blind spot.
Wow, so we've gone from the nightmare of forced manual alignments to the elegant simplicity of the collapse rule, and all the way to the boundaries of conditional independence. I want to leave you with this final provocative thought to really test your knowledge before your next interview. Can you comfortably explain the collapse rule and exactly why the CTC loss function is entirely alignment-free? If you can visualize those overlapping paths and articulate the absolute necessity of the blank token, you have fully mastered this study guide and you are ready. Thanks for letting me explain this to you, and keep on learning.